Barbara here to talk to us. He is a senior PhD student working in natural language processing and knowledge representation, deep learning. And he's done a string of internships at exciting places and published a bunch of cool papers. So we're going to get a view of that work today. He's going to talk about knowledge-grounded NLP. I'm just going to remind you that we're recording this presentation, and by convention, it's okay to interrupt with clarification questions that you think will be quick, but we'll ask that we save bigger questions for the end of the talk. So without further ado, welcome, Wenhu. We're looking forward to hearing from you.
Hi, everyone. My name is Wenhu. Nice to meet you guys virtually. So I'm very honored to be invited here to talk about my dissertation work on knowledge-grounded natural language processing. So first of all, I will try to give some credit to Pradeep, because this title was kind of inspired by his thesis topic. So yeah, thank you, Pradeep. Let's get started now. Feel free to interrupt me if you have any clarification question. So I guess most of you have had some experience with, like, say, virtual assistant, for example, Amazon Alexa, Google Home, so on and so forth, which you can communicate with using natural language for a certain purpose, like answering a question, schedule an event for you, chit chat with you, so on and so forth, right? And because I'm a basketball fan, the typical question I'm going to ask the virtual assistant will be like, what is the average points per game of LeBron James in 2019-20 season, right? Assuming you are the virtual assistant, in order to answer this question, there are lots of grounding. You need to ground on the external web knowledge to understand that LeBron James is actually an NBA basketball player. During the year of 2019-20 season, he was playing for LA Lakers, and the points per game of him is 25.3. And then you need to further ground on this piece of information to generate a natural language response, and then use this to communicate with humans. And from this example, we show that in the real world application, there are lots of knowledge grounding going on, right? If you're going to build a good virtual assistant. So that's why I kind of invent this term of knowledge grounded natural language processing. And specifically, I will try to divide this into 3 different parts. And the first part is called grounded understanding, where we need to rely on incorporate external web knowledge to understand the semantics of human natural language input, right? And once we ground on this web knowledge, we need to do some knowledge reasoning over, this diverse forms of knowledge to, derive what is the supporting fact for answering a given question, or, carrying out a specific action. And finally, we will need to ground on the supporting fact to generate natural language response, and then use it to communicate with humans. And what are the specific challenges for designing knowledge-grounded NLP systems, right? So in today's talk, I'll be mainly discussing 3 different aspects. So the first one is explainability, which means that we hope that the model should be able to lay out what kind of knowledge it is grounded on, to lay out its decision, why it makes such certain decision, right? And the second thing is that the web, especially the external web knowledge, is comprised of data of different modalities and different forms. We hope the model should be able to understand this heterogeneous data of different forms, and then integrate their information to make a smarter decision. And finally, we hope the model should be faithful to the external world knowledge rather than hallucinating non-existing facts, like LeBron James is playing for New York Knicks and stuff like that. And in today's talk, I will be mainly organize it through these 3 different aspects, or 3 different challenges. And then in the first section, I'll be talking about the knowledge, this explainable reasoning over knowledge graph. And in the second section, I'll be talking about efficient reasoning over heterogeneous web data. And finally, I'll be talking about faithful knowledge-grounded text generation. So these are the 3 different sections that we'll be going to cover in today's talk. And let's move on to the first section. So this is the problem setting of the first section, where we are trying to answer simple questions. So by simple, I mean these questions has an answer as an entity or relation explicitly encoded in the knowledge graph. And then the evidence we're going to use are this large-scale knowledge graph like Freebase, Nell, Yago, so on and so forth, consisting of millions of entities. Right? And the goal of this section is to come up with a model which is able to deduce explainable logical rule over a knowledge graph. And this work was published at NACO 2018 and this work was done at UCSB NLP group with my collaborators. And let me first lay out some of the background about knowledge graph. Right? So the existing popular knowledge graph like Freebase, WordNet, they are highly incomplete because they were constructed from the web data, and there are lots of missing links in this knowledge graph. Right? And according to a recent paper in the Google Freebase, 95% of the person don't have a birthplace, and 80% of the person don't have a nationality. So this means that the model, right, and so the knowledge graph can only encapsulate a tip of iceberg over the external world knowledge. And so here is a typical example, right? For example, we have some knowledge about LeBron James, Cleveland Cavaliers, NBA, and so on and so forth. And we are interested in understanding whether LeBron James has ever played for Cleveland Cavaliers or not. However, this relation or this link is not captured in the knowledge graph because it's incomplete. And so this problem is normally referred to as the knowledge graph completion or knowledge graph reasoning, right? Which can be formulated as a maximum likelihood problem where the starting entity is the LeBron James, while the destination entity is Cleveland Cavaliers. So these are the two conditional variables we put into the function, and then we try to find out what is the relation that maximizes this function. And in order to address this knowledge graph reasoning problem, right? And the traditional AI community proposed this first order logic algorithm, like back in old days, where they try to hire lots of domain experts to write these hard logical rules. And then they use these hard logical rules to deduce these missing facts. However, this can be very expensive. So that's why like the recent community proposed this soft logic, right? Where they try to use template to automatically generate lots of potentially correct logical rules. And each of the logical rule is associated with a weight between 0 and 1, indicating how much trust we can put on this logical rule when we are applying this into a real world situation. And however, in the deep learning era, so the state-of-the-art performance is achieved by this embedding method, like trans-E, trans-R, so on and so forth, which tries to represent each of the entities and relations as vectors, and then do reasoning in the vector space. So as we can see from the previous slide, right? So the soft logic framework, it has very strong explainability because it tries to lay out what kind of logical rule it is grounded on to explain its decision making, right? While the best performance is, however, achieved by this embedding method, which is more generalizable to large-scale knowledge graph. However, it's more like a black box, and the reasoning is done in the vector space, which means that we couldn't explain it. So the goal of this section is to design a deep logic network, which is both good at explainability and generalization. So let's move on to how we can do this, right? So the first step is to replace this maximum likelihood objective function with a maximum marginal likelihood distribution objective function, right? By assuming that there is a latent variable, which is the logical rule connecting the starting entity and destination entity. So in this marginal likelihood function or objective function, we have two parts. One part is the prior distribution, which is implemented with the rule discovery network. And the other part is the likelihood distribution, which is implemented with weight assignment network. And this rule discovery network will traverse the knowledge graph to propose what is the most informative and what is the most meaningful logical rules, right? That's connecting the two entities. And the weight assignment network or the likelihood distribution will give a probability, right, indicating how much trust we should put on this logical rule. So from this, this framework, we can see that this is directly a neuralized version of soft logic framework. And however, this marginal likelihood is very hard to be optimized, because when we're dealing with a large knowledge graph, there are normally like hundreds of thousands of logical rules connecting two entities, especially like in freebase, NL, and so on and so forth. So directly calculating this marginal likelihood or explicitly computing the likelihood is very expensive, making this optimization quite intractable. So that's why we resort to the variational inference. So instead of maximizing this likelihood, we're maximizing its evidence lower bound as a surrogate objective function. So this is how this ELBO is formulated. So this ELBO introduces a posterior distribution. So this posterior distribution is very similar to a prior distribution in a sense that they are both proposing like logical rules between the starting and destination entity. But the posterior distribution takes the relation as the input, while the prior doesn't take it. So let's zoom into this ELBO to see what does it mean, right? So this ELBO is consisting of two different parts. So the first part is called reconstruction likelihood, and the second part is called KL divergence. And in this reconstruction likelihood, we are giving a relation to a posterior distribution, and then let the posterior distribution to sample the most informative logical rules. And then we fit this logical rule to the likelihood distribution or the weight assignment network. And this weight assignment network should be able to reconstruct the original relation that we fit to this posterior distribution. And the second part is the KL divergence, which aims to minimize the discrepancy between the posterior distribution and prior distribution by pushing their distribution closer to each other. So that's like the breakdown of this ELBO, objective function. So let's see how we can neuralize this framework, right? So for the posterior and prior distribution, we were using LSTM. So this LSTM will encode the history of this compositional logical rule, and then try to traverse the knowledge graph to see what is the possible next step action, and then use the multi-layer perceptron and softmax to model this policy, probability or transition probability. And then once our posterior distribution samples several logical rules, and then we can use the convolution neural network to convolve the features out of these logical rules, and then make a prediction with respect to all the relations we have previously defined. So this is the likelihood distribution. Now we like neuralize all these three different distributions with networks, right? We can train our model by this parametrization. So we will update the neural network parameters of these three different modules to maximize the evidence lower bound.
Quick question.
Mm-hmm.
In previous slides, it looked like L was a single logical rule, but now it looks here like it's several. Can you clarify what that is?
Mm-hmm. Yeah, so we will use the posterior to, so here, so the evidence lower bound is, an expectation. So we will try to use Monte Carlo to sample multiple logical rules. And the convolutional neural network will take in, multiple of them to make an assemble decision. Yeah. So here, like after we train our model, so this is how we do the inference. For example, we are still interested in the relationship between LeBron James and Cleveland Cavaliers, right? And then we can use our prior distribution to traverse the KG and then take the most likely steps at each of this, decision. And then, traverse the KG to find out what is the most likely logical rule connecting the starting and destination entity. And then we will try to fit this compositional logical rule to our likelihood distribution, and then classify it to, one of the predefined relation. So this is what our model actually learns, right? So we try to prompt the model to see whether the learned logical rule makes sense or not. So here we set the LeBron James and Cleveland Cavaliers as the starting and destination entity. And then we use our posterior distribution to sample the most likely logical rule. And this is the one it discovers. LeBron James was coached by Tyronn Lue, and Tyronn Lue was the coach of Cleveland Cavaliers. And our model says that there are 98% confidence and this logical rule will hold the truth. And it makes sense, right? Because if you are playing for a certain person and this person is a coach of a team, then it's very likely that you're playing for that team. And then we let the posterior distribution to sample some less likely ones. So this is the one that discovers like LeBron James plays in the stadium for Rocky Market Center, and this Rocky Market Center is the home stadium of Cleveland Cavaliers. And our model thinks that there are only 42% confidence in this logical rule. And it also makes sense because the Rocky Market Center is also used for National Hockey League and the WNBA. So it's reused by different teams. So by simply looking into this logical rule can now sufficiently prove that LeBron James is playing for Cleveland Cavaliers. And then we further let this posterior to sample some unlikely ones. So this is the one that discovers LeBron James is playing for NBA and Cleveland Cavaliers is a team in NBA. And our model is only putting like 8% confidence in this logical rule because there are lots of teams in NBA, right? By simply looking into this logical rule, it doesn't imply which team LeBron James is actually playing for. So from this, human inspection over the model's learned soft logical rule, we can think we think that the model is actually working well, and then we move on to the link prediction task and compare with the other state-of-the-art models. So the data set that we use are free-based and now. Both of them can be formulated as given two entities and predict the relation. And there are mostly tens of thousands of entities in this knowledge graph. And on the NEL data set, we're measuring this mean average precision, which means that how much percentage of the relation, top one relation is the ground truth relation. And we can see that our model is getting on-par performance with the Minerva model and outperforming the other baseline models at that time. And on the free-based data set, our model is better than the state-of-the-art model of DeepPath by 2.6% accuracy. And at the time, our model, the paper was proposed, we got this state-of-the-art performance. And so the takeaway message of the first section is that we try to propose a model that can deduce explainable logical rule and is also scalable to large web knowledge graph. And we're getting so top performance on different link prediction data sets. But what's next, right? So in this section, we are only focused on very simple relational entity-based questions that we cannot cover very complex free-form questions from the user. And on the other hand, because this knowledge graph are constructed from the web, it has lots of disadvantage. For example, it's highly incomplete and it can be stale and it can be noisy, right? So how can we leverage massive amount of heterogeneous raw data from the web to do a question answering? So that's why we move on to the next section, and it motivates me to do this paper. And so this is the second section. The problem setting is that we're answering more complex questions. So these questions are normally multi-hop questions, like what is the average points of LeBron James in NBA season suspended by COVID, something like this, right? And what we have here as the evidence is not the knowledge graph. It's actually the Wikipedia, which consists of both unstructured and structured knowledge in the form of documents, lists, tables, and so on and so forth. And the goal of this section is to design an efficient QA model that can reason over heterogeneous web knowledge. And this paper was accepted to ICLEAR 2021. It was done at Google AI with my collaborator, Mingwei Zhang, Eva, and William Cohen. And first, let me lay out some of the background knowledge about this open domain question answering. and it was proposed by Chen et al. In 2017, where it takes in a question and then try to use, let's say, TF-IDF, BM25, or whatever retrieval system to browse this Wikipedia and then retrieve the passage with highest lexical overlap, and then do a reading comprehension on top of this passage to extract the span which best answer this question. So this can be a very strong assumption by assuming that a passage can answer a given question, right? In the real world application, we actually don't know what is the knowledge source in prior, right? We're taking the questions from the user. So assuming that we're dealing with this complex question of what is the average points of LeBron James in NBA season suspended by COVID, if we are going to still going to use this text-based framework, and then we can retrieve multiple passages about LeBron James 2019 to 2018 season, the COVID pandemic, and so on and so forth. But still, we are not able to find any span in these passages which can actually answer this question. And our model might say that this question is unanswerable. However, this is actually not the case. If we go an extra mile to retrieve the table from a LeBron James webpage, we will get this LeBron James career statistics, and the answer is actually in the cell of the table. And the answer is 25.3. So from this example, we can show that in order to build a good, a virtual assistant that can reason across the whole web, we need the model to have some kind of ability to handle heterogeneous web data. So the goal of this section is to design a unified QA model that is not only able to understand unstructured and structured data, but also able to integrate that information as a whole to make a smarter decision and derive the answer. So however, at the time we were doing this, we're trying to solve this problem, there's no data set for training and evaluation. That's why we proposed to collect our data set to drive this direction, this research direction, which we call as the open turbo text data set. And we try to browse the Wikipedia to crawl this, regular tables with, without very weird symbols and stuff like that, and then use the hyperlinks within this table to request what are the highly relevant passages for understanding this table. And then we fit both the table and passages to the Amazon Mechanical Turker and let them write question and answer pairs. And then in order to do this quality checking, the first thing we did is that we try to deploy a model to make sure that the question is actually requires integration of information from both sources. And then after this, approximate filtering, we also hire some human experts to make sure the question and answer pairs are grammatically correct and fluent. So at the end of the day, our OTT-QA dataset contains of question answer pairs of 45,000. So here is the problem setting of OTT-QA. So we are taking a question, and then we have a heterogeneous candidate pool. So in the candidate pool, we have 5 million passages and 2 million tables. However, we mask out these links between passage and table to make sure that our model trained on Wikipedia can be used in other domains, right? Because these hyperlinks are so specific to Wikipedia. So we want to simulate a more general case where we don't actually have these hyperlinks. And in order to address this problem, we need to train two things. One is the heterogeneous retriever, which trains this relevance function, which takes in a block in the heterogeneous candidate pool and the question, and then try to output a probability between 0 and 1, indicating the relevance between the question and the block in the candidate pool. And then we will use this retriever to retrieve the top K blocks from this candidate pool. And then we fit this top K candidates and the original question to the heterogeneous reader to extract the span as the answer. So in the previous text-based QA, right, we're only dealing with the passages. So the complexity is roughly in the order of 5 million. And now, because we're considering two modalities and their interaction, right, So we are suddenly dealing with a problem with much higher complexity of 5 million multiplied by 2 million. And that's why the efficiency is a big issue here. So how can we make sure that our model is as efficient as the text-based QA? Right? So let me first introduce some background about this retrieval part. Right? So now the state-of-the-art retrieval is actually based on dense retrieval rather than BM25, where it uses this neural network, which is called candidate encoder, to scan over the whole candidate pool to encode each of the documents or whatever into a fixed dimension vector. And when there comes a question, we will use our query encoder to encode it also into this fixed dimension vector, and then use the maximum inner product search over this whole bank of millions of fixed dimension vectors to get its nearest neighbors. And the time for one time of query is roughly in the order of like 100 milliseconds to 2 seconds. It's kind of expensive compared to BM25. So now let me introduce some the baseline system that we're using, right? So the traditional way, because we are answering multi-hop question, which requires reading multiple blocks. So the standard way of doing this is by decomposing this into an autoregressive procedure. For example, it needs to read 3 blocks, and then we will first retrieve B1, and then B2, and then B3. So what we did is that, so we will first ground on the question, encode the question, and then retrieve over the candidate pool to get K1 nearest neighbor. So this is denoted as B1. And then we will re-encode B1 and Q, and then do re-retrieval over the candidate block to get K2 candidate nearest neighbors. And then we will re-encode B1, B2, Q to do the last round of retrieval to get the K3 nearest neighbors. We will continue this procedure until we accumulate enough blocks, for example, K blocks here. And this can be very expensive because we are doing repetitive, re-encoding and re-retrieval, right? So the time complexity here is OT plus OK1T plus OK1K2T. And this is in the order roughly in OKT. And in open domain question answering, we are mainly dealing with the K roughly in the order of 50 to 100, right? So the T is roughly in the order of 1 second, so this can be extremely slow. That's why we try to, simplify this procedure to make it more efficient. So this is how we propose this relaxation. We will still use the autoregressive decomposition, but in the first place, we will try to do some relaxation to temporarily remove B2 to BI's dependency on Q, but we still keep B1's dependency on Q. So for example, so in this case, we can see that the following B2 to BI's retrieval doesn't depend on Q. So we can do this offline, right? For example, we can train a model that can be conditioned on B1 to retrieve B2 to BI. And then we have this mapping between B1 and B2 to BI. We can group B1 to BI as a basic retrieval unit and jointly encode them as if they are one document, right? And by doing this group retrieval and joint encoding, we are actually recovering the dependency between B2 to BI on Q. So now it means that we actually didn't lose anything. This is how we implement our model, right? So for example, we have a B1, which is a table, and then we will use off-the-shelf entity linker to find out what are the highly relevant passages, which are denoted as B2 to BI, right? And then we aggregate B1 to BI as a single grouped block here, we call it. And then we apply this merge strategy to add each and every block in the candidate pool. So now we have several millions of grouped blocks, right? And now we can use our neural network to compress each of the group block into a fixed dimension vector. And when there comes a question, we only need single step of retrieval over this grouped block without any, autoregressive retrieval and stuff like that. Now, by doing this, we are able to lower the complexity from OKT to OT plus O1. And this makes the model much more efficient. And once we retrieve this, top K evidence blocks, right, we need to fit this into our reader. So the state-of-the-art reader is called BERT, right? So it will extract the span from this evidence blocks to answer the question. So however, we're dealing with lots of blocks. If we're gonna linearize all this information and then put them into sequence, we can easily exceed the length limit of 4,000, right? We're dealing with 4,000 tokens. And it's worth noticing that the BERT model uses a full attention mechanism, which has a capacity of all k squared b squared. And this can be very slow, and the GPU memory is going to overflow if we are dealing with an input length over 4,000 tokens. So that's why the current researchers propose to decompose these long sequences of retrieved blocks into smaller groups to make sure that each of the smaller group has input token length within 500. And then it will feed all of this, small groups to BERT independently and in parallel, and then we'll select the one with the highest confidence as the final answer. So this is kind of disadvantages in a sense that it fails to capture or model the global context, and the prediction is actually a local optimum. And so in this case. So that's why we use this global local sparse attention to make sure that we can capture the global context. So what we did is that we try to decompose these long sequences to lots of blocks, depending on where this token actually comes from, right? So we decompose this long sequence into K blocks, and then for each of the block, we will annotate a global token in the front. And now this global local sparse attention consists of 4 different parts, right? So the first part is local to local attention, which means that each of the token within the local block can only attend to its neighbor local tokens. It cannot go across the boundary. So this has a complexity of KB squared. And then we have global to local attention, which means that the global token will try to summarize information from its assigned local blocks, right? So now each of the global token will have an overview over the whole local block. And then we will have global to global attention, where the global tokens will interact with each other, so that at the end of the day, each of the global token will have a summarized information over the whole sequence. And finally, we have this local to global attention, which means where we allow these local tokens to attend to all the global tokens, so that each of the local token will also have a global context. So by doing this 4 types of attention, we are able to, all these attentions are sparse. Even if you are adding the capacity together, they're actually in the order of all KB squared, which is lower than K squared B squared. And the bonus is that each of the representation for each of the token, it captures some kind of a global context. So with this, sparse attention model, we can fit in all of this top K blocks at once to the model without any decomposition. And we are able to deal with sequence lengths over 4,000 tokens. And the other thing is that we can model the global context, and the prediction is actually a global optimum. So here we try to evaluate different models for the OTT-QA test set. And so these are the baselines, right? So the very basic ones using BM25 and different types of readers. So, and the first baseline that is what we have proposed before in this section, right? Using this multi-hop autoregressive retrieval plus this BERT reader with decomposition mechanism. So this is not getting a very good score. It's only getting 10% accuracy. If we are going to replace this multi-hop retrieval with the fusion retrieval, where we try to do this group-wise retrieval with one step, we're actually improving the performance by a lot, from 10% to 17%. If we're going to replace the BERT reader with a sparse reader, because we're able to model the global context, we can improve the score to 14%. if we're going to combine the Fusion Retriever and the Sparse Reader, we can achieve a score of 28%, which is much higher than all of the baselines that we have discussed before. And we also did some efficiency study here, right? So the bonus that we get here is that our Fusion Retriever is in average 8 times faster than this multi-step retriever. And our sparse attention model is twice as fast as the BERT reader. To prove the generalization of our model, right, we also evaluate our model on HOP-QA. So what we did is that we just replaced all the tables with passages, right? We can still do the same thing as grouping and sparse reading, right? And so these are the baselines that we're comparing with. So some of them are the state-of-the-art model at the time the paper was published, like an IN retriever transformer, XH, and so on and so forth. So we end up getting on-par performance with the state-of-the-art model. But the bonus is that we don't have any re-ranking over the retrieved blocks. So our model runs much faster than the previous state-of-the-art model. For example, in the INN retrieval model, it requires the BERT re-ranker to rank like 200 reasoning chains. So our model doesn't have this extra step. So it runs much faster than the IN retriever. So now let's move on to the last section of faithful knowledge-grounded text generation. So this and in the previous sections, right, we have already covered how we can do grounded understanding and how we can reason over heterogeneous data and integrate informations on the web, right, to derive this supporting fact. And to close the gap, we still need this grounded generation to actually generate natural language sentence to communicate with humans. So this section is exactly focusing on this part. And the goal of this section is to come up with a faithful text generation model over the world knowledge. And this paper was published at NLP with my colleagues at UCSB NLP group. And in order to solve this problem, there have been already lots of data sets being proposed, which assumes that knowledge is taking different forms like chart, key value pairs, knowledge triples, tables, so on and so forth. And the text could be a report, could be a dialogue, description, biography, so on and so forth. And the state-of-the-art model to address this wide spectrum of data to text generation problems is called GPT-2, which consists of 36 layers of self-attention and have 700 million parameters. And in order to train this model, that OpenAI has created a web text data set, which consists of 40 gigabytes of text. And they propose this next word pre-training objective where they fit a prefix of the sentence to the model and then let the model generate what is the next word, right? So for example, LeBron James plays as a power forward at, and the model should be generating LA Lakers. So what this model does is actually it's trying to compress the world knowledge into the 700 million parameters, and then let the model memorize all of them in their language model. So this GPT-2 model, since it was proposed, it has attracted lots of attention because it can generate very natural and fluent natural language sentences. So this is an example that I found on the OpenAI blog. So a chain carriage containing controlled nuclear web materials was stolen in Cincinnati today. Its whereabouts are unknown. So these are the human written prompts we feed to the GPT-2 model, and then let the GPT-2 to complete this story. And then the GPT-2 model will generate things like the incident occurred on the downtown train line, which runs from Covington and Ashland stations, in an email to blah, 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 right? So at the first glance, we are not able to tell whether this story is actually composed by a system or by a human. So at least for me, I cannot tell. But however, if you zoom in a little bit closer, and then, for example, this Covington and Ashland station, I try to Google it, it doesn't exist in the world. So which means that the model is actually hallucinating this non-existing facts. So this hallucination problem is very severe for this GPT model. So the hallucination comes from two different sources, right? So the first one is the mismemorization, which means that the model actually sees this information, but it fails to capture it in the parameters. For example, we can fit some prefix and then let the model to complete this sentence. The model thinks that Taylor Swift was born in the year of 1859, and the model thinks that Microsoft was founded by John McAfee. The model thinks that Christmas is in the month of October, so on and so forth. And we try to curate like 100 very frequent and very common factual knowledge, try to prompt the GPT-2. And it turns out that the model can only get 20% of them correct, while the rest of them are just hallucination. And the other source of hallucination is called Stale-Memorization. Assuming that we are pre-training the model using 2017 Corpus, right, which we scraped from the web, which contains lots of documents connecting LeBron James with Cleveland Cavaliers. So our model put very strong language prior between LeBron James and Cleveland Cavaliers. So if we're going to apply this model in 2021, after LeBron James was already transferred to LA Lakers, and then we let the model to generate some, text, it will generate things like LeBron James led his team Cleveland Cavaliers to win the 2020 NBA championship. So because this model has very strong prior, it's not very easy to get rid of, right? Unless you pre-train it, this could be very expensive. So in order to solve this problem, we try to first zoom in to see what kind of knowledge the GPT-2 is actually memorizing, right? So here, from my understanding, GPT-2 is memorizing two types of knowledge. So the first thing is how to speak. So this contains implicit linguistic knowledge in terms of how to compose words into a fluent and natural language sentence, right? And the other part of knowledge the model is trying to memorize is what to speak. It's basically explicit factual knowledge, like Bill Gates founded Microsoft and so on and so forth. However, this factual knowledge can be infinite and it's not always static, right? So it doesn't make sense for the model to memorize all of them. So therefore, in this section, we're trying to disentangle this factual knowledge as the input so that the model is discouraged to explicitly memorize them in the parameters. It will only ground on this input to generate natural language sentence. So this is how we do it. So we propose this KGPT model, and then instead of doing unconditional pre-training, we're doing conditional pre-training. So we're still using the transformer, but we have a much smaller model with only 6 layers because we don't need to memorize stuff. So the parameter size can be decreased. And we are still using the same objective function of predicting the next word, right? So the big difference here is that we will provide the most relevant knowledge with respect to this given sentence. So the model is able to ground on this relevant factual knowledge to generate this next word without memorizing this. And the bonus that we get is that we are able to compress the model from 700 million parameters to only 100 million parameters. So you might wonder how we can train this model, right? So this is not easy because in the GPT models, we are only feeding the text to the model. Now we need to fit both the text and the knowledge which supports this text, right? So what we did is that we try to automatically construct this KB to text data set from Wikipedia. So what we did is that we browse the Wikipedia page and then we know this hyperlinks, right? And then for each of the sentence, and there's the hyperlinks, we use them to query the Wikidata, which is a large knowledge graph, which has correspondence to the Wikipedia. And then we will have the surrounding nodes, right, in the large knowledge graph in terms of what are the neighbors of these entities. And then we try to merge these different entities and construct a local knowledge graph. Presumably, this local knowledge graph will contain enough information to support the generation of the original sentence. And we do some filtering to make sure that the lexical overlap between this constructed local knowledge graph and the sentence has lots of overlap to make sure they are mutually supported. And then we do some decontamination to remove the these pages which might conflict with the downstream data set we are experimenting on. So at the end of the day, we harvest 7 million pairs of KG to text, and we call this as a KG text pre-training corpus. So what we did is that we use these pairs to do this conditional language model pre-training. And then after a few epochs, we can get this pre-trained KGPT model. So this is very similar to GPT. And then we can probe it, right? So now instead of letting the model to do generation from scratch, we can do controlled generation. So let's see. So for example, if we are interested in generating stuff about, let's say, Taylor Swift, right? We can traverse the wiki data to sample some of the two-hop, facts surrounding, Taylor Swift and construct a knowledge, local knowledge graph. And then we fit this local knowledge graph to the KGPT, and then let the KGPT to randomly generate things. Now the model is able to get things correctly. And the Taylor Swift, it will generate things like Taylor Swift is a female singer born in 1989. Taylor Swift was born in Pennsylvania, United States, and so on and so forth. Right. So from this experiment, we can see that the faithfulness of the KGPT is greatly improved over the GPT baseline model. So the other thing is that once we have this pre-trained model, right, we can actually do transfer learning to different data to text generation tasks. For example, this Wikibao dataset, WebNLG dataset, or E2E-NLG dataset. They're using different knowledge as the data, but it can all be encoded as graph, so we can transfer our model to that, to these models, to these datasets. So one thing that we tried is the full shot transfer learning, where we use the full data set of this downstream data, the full 100% of the downstream data set to see how much our model can achieve. So on WebNLG, if we're gonna use all of the data, our model can achieve 64% blue force score, which is 3% higher than the state-of-the-art model, and then also than the GPT model. So, and the other experiment that we try is the few shot experiment, where we try to only transfer by using only a small amount of the examples in the downstream data set. Like let's say on WebNLG, we only use 0.5% of the data of the data set to transfer the knowledge. And our model is still able to maintain like 22% blue score, while the GPT will be going down to 8%. And on E2E-NLG, our model is 40%, and the GPT model is 22%. And from this example, we can show that our model is very good at transfer learning. And now back to the faithfulness, right? We try to let the model to generate text on the WebNLG dataset, and then classify the generated sentence into 3 categories. So the hallucination, incomplete, and precise. And we can see that the GPT model actually can improve over the baseline non-pre-trained model on the hallucination from 18% to 14%, decreased by 4%. If we're going to use the KGPT model for WebNLG, we're able to lower the hallucination from 14% to 6%. So this is a significant, jump in terms of decreasing of the hallucination. And so this is a table comparing GPT-2 model and KGPT. We're using less parameters, but we're actually getting the same fluency and same transferability. Our model is more faithful to the given more knowledge and has better controllability. But however, the GPT model, because it doesn't have any condition, it trains on much larger corpus, it has better diversity, and is in terms of generating more fine-grained text, while our model is not able to generate such a diverse text. So we leave this as a future work to explore. And so this is a wrap up of the first 3 sections. So in this first section, we design a neural system that can reason over knowledge graph by learning to deduce explainable self-logical rule. In the second section, we design a neural system that can reason across heterogeneous data at web scale efficiently. Finally, we design a pre-trained paradigm that can faithfully ground on more knowledge to generate coherent text. And now back to the main problem of knowledge-grounded NLP, right? So one of the core things that I care about is memorization and the retrieval, right? versus retrieval. There has been lots of successful attempts to prove that actually the model can memorize lots of stuff like BERT, GPT-2, GPT-3, and so on and so forth. And some of the researchers go to the other extreme to say that we should retrieve everything. So some examples are like entities, experts, realm, large, FAE, so on and so forth. And so there are, two parties, thinking in different ways. And it boils down into the philosophical problems of when should we memorize and when should we retrieve. And from my understanding, for those explicit raw knowledge, which can be readily encoded into data, because it's infinite and it's constantly changing, it's probably better for the model to retrieve and read them. Right? But however, there are a large amount of knowledge which is implicit and cannot be readily encoded into data. For example, like common sense, right? Like temporal knowledge, social knowledge, linguistic knowledge, so on and so forth. It doesn't make sense for the model to retrieve them. So it's better for the model to memorize and generalize them in a subconscious way, right? And so this is the future NLP blueprint that I envision. So in the future, so the raw knowledge might be disentangled to its implicit part and explicit part. Our model is able to memorize the implicit part and also retrieve this explicit part. So instead of doing this knowledge-grounded NLP for just question answering, right? We can use this model, this unified model to whatever NLP task. But each of the tasks has some degree of retrieval and has some degree of memorization. So for example, the question answering is more like a retrieval-based problem, but it can get some information flow from memorization. For machine translation, it's more like a memorization-based problem. And then, but however, if you're gonna retrieve something, it will also improve the performance. So that's why I propose to, leverage the skate, right, to control how much information should flow from retrieval and how much information should flow from memorization. And in terms of the future directions that to go, and so these are the 4 things that I'm super excited about and I want to explore more. So the first thing is, how can we leverage the visual knowledge also into our model, right? So in the talk, I've been discussing about structured and unstructured knowledge, but they are all encoded in textual format. So how can we leverage visual knowledge? And the second thing is, how can we design a unified representation over all this unstructured, structured, and visual knowledge, right? And then use it to address all kinds of knowledge-intensive tasks. And the third thing is, I'm currently working on the third thing is that how can we deal with the contradiction across different knowledges, right? So if we're going to scale up our retrieval to the whole web instead of just the Wikipedia, there will be lots of people writing passages about LeBron James, and people have different opinions. And some of them are even adversaries. They try to propose fake content there. So how can our model deal with such kind of contradictions and duplications of different knowledge that we retrieve from the web? And the last thing is, how can we even ensure and verify the authenticity of the web knowledge, right? There are lots of false claims and wrong knowledge from the web. So how can we use things to cross-validate this knowledge before we even use them? So besides this knowledge-grounded NLP, I'm also interested in let's say multi-model problems which bridge the gap between vision and language. I've been publishing papers in visual question answering, image and video captioning, and video-based fact verification, so on and so forth. And I have also done work in multilingual problems like machine translation and cross-lingual transfer. But I don't have time to cover this aspect in today's talk, but I'm happy to discuss this offline. And yeah, that's it for today's talk. Thank you everyone for attending. So let's move on to the Q&A section.
Thank you, Wenhu. Thanks for the great talk. I think we have time. We have time for maybe 1 or 2 questions. I want to make sure our guest gets a minute to catch his breath before we move on to meetings. But please jump in.
Hi, I have a question. This is on the third part of your talk where you were talking about KGPT. And I was a bit surprised that your only baseline there was GPT-2, and I wondered how this compares to, for instance, KGLM or NoBERT or Ernie or a bunch of other methods that tried to do similar things.
Oh, so we also compare with some non-pre-trained models, basically using LSTM and stuff like that. For Ernie, I'm not sure if it's able to generate text. Right? It's and KGLM. So I think both of these models are natural language understanding models. They are not autoregressive language models to generate.
KGLM is an autoregressive language model.
Okay, I see. So I haven't looked into that, but
okay.
The Ernie, right? Yeah, I looked into that. I think it's more like an NLU model. Okay. Thank you for the advice.
I had a quick question as well on the third part. So in principle, if you were to modify the knowledge graph to have incorrect facts then the text that's generated should reflect those incorrect facts. Did you test that to see if that actually happens?
Oh, that's a good question. We haven't tested that. But definitely we need to see like whether this actually controls the generation. Right? Yeah, so that's a good suggestion. Is there any other questions?
More questions? Okay, let's thank the speaker again and give him a minute or two's break before he gets grilled by the next meeting, which I think is me.
Okay.
Thank you.
Thank you, everyone. Yeah. Nice to meet you guys. Bye.
Okay, so I'll see you in a minute or two, and you have the link to the other meeting, right? Okay.
Yeah. Cool. See you then.